the, right, so we have the URL in the bottom of the screen here for the instructions and the slides. All right, so we'll be using the do block later in this half, but this was an error. So let me just quickly go back how apply function is defined. It's a function that takes in another function and applies the value x to that function, right? So it's a really silly little prototype, but I think you get the point. Now, and we had looked at this case where we pass in an anonymous function, right? So this is just a function that increments the input. And I'm going to do the same thing with a do block. The idea here being, what if your anonymous function needs to be more complicated? If you are thinking about Python, what if you needed a multi-line lambda, right? And that's what the do block does. It does look a bit weird because the apply function now only has one argument, but this isn't a function call. What the do block does is it takes whatever is inside the do block and applies it to the first variable of the statement that precedes the do block. When we do I/O, it might make a little bit more sense. It's a little bit like a mixture of of when in Python and some additional concepts. All right, so with that erratum out of the way, I also wanted to address this question about what the biggest advantage of Julia is, in my opinion at least. If you remember, I was showing this slide of a real-time data processing workflow, and I was trying to motivate the idea that we need to be able to program on an HPC system in such a way that we can make rapid changes to the code and iterate through those rapid changes. So basically high productivity coding without sacrificing any performance. And that's that second bit about not sacrificing any performance is, I think, key here, because so we support many Python workflows. However, in order to maintain high performance, Python needs to be coded in a very particular way. So that means you will lose some productivity, and in this case it means in this step here, you might waste some time when you, for example, switch between compiled modules in Python, or when you try to debug some unusual behavior of modules like number. And so I actually have this as an example here. Oops. Oops, let's go back to the beginning. Skip this the last time, but I think this is a neat example where we're going to use Numba, which is a tool in Python that also uses LLVM to compile code. So this is our problem. It's basically a weight on a spring with drag. And so in Python, your code might look like this. I remember this might be a bit hard to read, so let's zoom in. I think this is easier to read now. Oops, it's the wrong screen. So here we have a function that defines our friction. It's a little bit of an unusual friction function, but it tries to get the point across of something non-trivial. And then we create our data arrays, and then we have a for loop that steps over each individual time, applies the friction, and essentially solves Newton's equations here. Okay, and so now we try to plot this, and what we see is a sort of a damped oscillation. Sorry. I think the zooming in sometimes breaks the formatting a little bit. And so, oops, I'm sorry, this is the, here we go. So if I now try to run this code, you'll see, I mean, basically just remember this is a benchmark. We've spent about 232 milliseconds running our particular example. Now we can do this, we can take this Python code and convert it to Numba. So we import Numba JIT. Okay, the problem with zooming in is then sometimes things don't fit on my screen. So I'm going to zoom out a little bit. And I apply the njit decorator to our Python code. I simulate, it's the same solution. And now I can compare the two benchmarks, and you can see that Numba has now decreased our runtime by about almost a factor of 200. So that's pretty cool. In this example, it's actually almost, this code here is almost unchanged. We really just have to apply this decorator. And so in this particular example, this is a problem that was really easy to convert to Numba. But this is a little bit misleading because many more sophisticated codes require significant changes for Numba to work. And so if we now did the same thing with Julia, I'm just gonna, so this is the Julia code for exactly the same problem. Yeah, we get a bouncy spring, and we can benchmark it. And the Julia code has a mean runtime of about 2 milliseconds. So on par, maybe a little bit slower, but that could also be an artifact of the benchmarking, but on par with the optimized Python code. So this is basically the takeaway message of this exercise, that unless you're doing something that's abusing the Julia language, you should be able to achieve, in many cases, performance equivalent to compiled code with Julia, which is roughly 100 to 200 times faster than Python on its own. And so that is really the biggest advantage of Julia, in my opinion, that if you are analyzing your data and you start to hit bottlenecks, in Python you have to do a lot of work to redesign your code. And if you don't have time to do that, then that can be a real issue. So I hope that has answered this particular question. And I'm going to do my best to make sure that we stay sort of zoomed in. Okay. I'm also, excuse me, I wanted to make sure that this stays up. I'm gonna shift some things around a little bit. Sorry. If this were Linux, I would know how to make it always stay on top. Okay, so I'm just going to skip over this. And so in the second half, we're going to focus a little bit more on data analysis kind of workflows. So we will skip the introduction to the Julia language. We've already done that. And then we will look at how to access different data, how to explore data, and then finally, we're going to look at machine learning, and also I think a very neat example of how machine learning is somewhat unique, I think, in the Julia language. So let's pick up where we last were in terms of array data types. So if you remembered, when we were looking at arrays, last time I said, well, what about, sorry, excuse me, Julia array started at 1, right? So you might have remembered this error message here. So let's look a little bit more about working with n-dimensional arrays. First of all, the size method gives us the dimensions of our array. This is pretty much the same as most languages, and whenever you place a loop inside square braces, then you will produce, so that will automatically initialize an array of whichever dimensions of your loop. And so in this case, we have a two-dimensional array being initialized. You might notice, and this is a pretty important difference to C-like languages, that, no, I'm going to mention something later in a second. I'm sorry, I'm skipping the gun here. But the point is, we're basically just, we can create multi-range loops just using the syntax where the for loop will have several ranges inside of it. Now, Julia uses column major data in memory. So it's more like Fortran than, what is it, C and Python. And one example is if you, for example, take this 2D array here, M, and I would like to get the Cartesian indices of this matrix. And I'm going to just iterate over all the Cartesian indices. The Cartesian indices function gives us an iterator that iterates in the most efficient memory access pattern. And so you can see I'm scrolling through the first index, and then I increment to the second index, right? So we are going down the columns, and then we will go down the next column and the next column. You can also turn a multidimensional array into a single one-dimensional array using slicing. So in this case, we are just applying a single slice to our 2D array, and it will unwrap, it will flatten these tuples that we've put into this array. Remember, this original array is really just a collection of tuples of int 64 type containing the two indices that we are putting in. And you can see it's unwrapped it, and we're going 1, 2, 3, and then 1, 2, 3, like so. So if you ever forget, that's the trick. Use the Cartesian indices and just explore what's happening. It's a little bit misleading sometimes also if you think about this notation here. You might think the first statement here before the comma is the inner loop, but it's not. It's the second statement. So if I just print out in which order are we going down this double loop here, you can see the I variable stays constant and the J variable increments. Now, if you think about how our data is laid out, that can result in a few issues, right? So if you try to use this to access the data, you would actually do it the wrong way around. So that was just a word of caution. Now, I wanted to demonstrate the effect that accessing an array in the wrong order can have on performance. So here we have one workload that iterates over the rows first, right? So we've got I and J. J is the inner loop. And so let's do a benchmark of that. We're getting a benchmark of, I'm just going to make sure that we can still see it. Okay, maybe this is even best. So we can get we're getting a total runtime of about 7.5 milliseconds. So let's iterate over columns. So what I've done, if you just look at these two, I've juxtaposed J and I. So I and J is now the other way around. Also, of course, you have to remember to juxtapose the limits. And now we're getting, rather than 7 milliseconds, we're getting 2 milliseconds. Obviously, the real numbers will vary depending on the details of the benchmark, but this just goes to show that you want to make the inner loop touch this touch the first index of our matrix. I also mentioned element-wise operations. I hadn't really covered this. There's the idea of taking a function and applying that to every element of a data structure is called broadcasting. So let's create a literal array again. So for example, here's one matrix. We can create matrices in various, using various notations. And so now we've got our 3 matrices. Now, previously, you saw that if I just apply the mathematical operators directly, then they're interpreted as the linear operator on the linear object. So, and I mean, this is what we would expect from from this operation, and also a matrix product is the product operator is the matrix product. By the way, if you were to look at the standard library, you would find that there's a function in the base module called asterisk, right? So this is the multiply function. Now, I could also, rather than doing a matrix product, I could do an element-wise product of all the elements within a matrix. The way I would do that is I would place a dot in front of the function that is being called, that you want to be called on each element. So in this form here, it's being, the first element is being multiplied by the first element of this one. The second element of M1 is being multiplied by the second element of M2, and so on. At some point, you might feel a little bit tired of having to put the dot in all the time. There is a macro that's just the @ symbol and a dot, and basically you can put that on any line of code, and it switches the mode to broadcast by default. So basically all the function calls are broadcasted, all the products, additions, and so on, they're all broadcasted. So if you see @dot, no one's swearing, it's really just people being a bit lazy. And as I said, broadcasting can also be applied to function calls. So here I have f being applied to a number. And I can either manually call the broadcast operation and say I'm going to broadcast f over M3, or I could just go f dot M3. Do I have an example? No. And by the way, being typed here is actually really helpful, because imagine I didn't put the number type here, and then I placed a matrix in here. This matrix, this would just be a matrix multiply, right? You would get a different mathematical object out of this. And so the compiler wouldn't mind, right? If I just write f of a matrix, it's valid code. But mathematically, it's different. So by placing this type annotation here, you would then invoke an error saying, well, you're giving me a vector of numbers. I only know f for number. And so then you immediately know what's going on. And finally, I want to also have a word of caution about abstract containers. So, for example, if I just create a vector object, it automatically creates a vector of any type. Any is sort of the root of the tree, of the type tree. So this is an abstract type, so you're creating a vector of abstract elements. This means that the compiler doesn't know to treat this as an array. It's going to be a list of pointers, and those pointers can contain anything, right? So so this will not do very well in terms of performance. The problem with any type collections is that if I fill them even with concrete types, the vector is still of any type. And worse still, I can start mixing and matching, so I can have, this is now really truly a list. Yeah. Yes. Okay, the question is, I had never thought about this. This is the function broadcast notation, right? It's f dot, so it's after the function. This is how you broadcast an operator. It's a good question. I don't know. I assume I'm going to speculate what one of the language designers would say, and they would probably say, well, it's actually the operator part of a function call is the bracket. The bracket is the call. The F is just the label. That's how I would say it, but I don't actually know if you know if anyone actually like made that decision consciously. This notation, I think, has been copied from the MATLAB notation. So it might be the case that MATLAB does it this way, and maybe, you know, decades ago, someone very smart at MATLAB just said, I'm going to do it like that. So we might never know. By the way, if you wanted to use the broadcast function on something like a linear operator, then this f would just be literally just the times symbol, and then you would put however many arguments you would need. So you can use this on the times function as well. All right, we have list. So yeah, basically, just to recap, a vector of any type, you can really think of it like a Python list. The problem is that we now have a collection of non-concrete type. And just to demonstrate that this can have a bad effect on your performance, I've created an abstract vector and a vector of float 64. I fill them with the same thing, and now I apply the square root. So for the abstract vector, we are spending about 370 microseconds. For the concrete type, it's only 45, well, yeah, 45 microseconds. So this is something that really is worth keeping in mind. Even though it might be convenient to just think, let's make every vector of any type. All right. So I think that I'm trying, oh, I should just go like this. Here we go. So now that we've sort of an overview of the language itself, I wanted to get slightly more applied and maybe look at some example notebooks as well. Let's see, also, if there are questions, let me know. I assume people can get onto the AHA slides. Just a reminder, the link is down here, and I think you can see it in the video. All right, so if we want to do any sort of data science, we need to somehow get to the data. And so the first step is usually to read from files. It might not always be where you're going to go eventually, but file I/O is, I think, fairly fundamental. And if you want to interact with a file system, I just wanted to have some helpful pointers here. First of all, the _dir macro gives you the current files directory, as well as _file gives you the full path. So in Jupyter, you would call the pwd function. You can actually call that function, but the sneaky thing is, imagine you're in a file in one directory, you've changed directories, and then you call pwd. That will then give you the pwd of the changed directory, right? Print the working directory. But often you want to define data as relative to somewhere, right? You have your analysis script, and like a folder called data in the same directory is where you keep your, I don't know, your calibration data, something like that. And so in that case, the dir macro is really helpful. And so, for example, if I just run it on my laptop, I would see a path like that. Oh yeah. Now, obviously, this path is in Unix format, right? So if you want to start working with paths in a way that's agnostic of your operating system, we have a bunch of functions available. The one that's probably most commonly used is the join path function. So here it's sort of a little bit of a depressing example, but in the same repository, 2 folders up, I'm pretty sure there's actually a up command, but I admit I forgot to add that here. But yeah, so we're going 3 folders up, going to exercises, COVID, and then there's a data folder. Okay, so that's going to be our data directory. And remember at the very beginning, I talked about make tempter. Well, I think it is sometimes very helpful to have like some sort of scratch space where all sorts of artifacts and you know, you can mess up. So I usually do something like this as well. So I've got a temp directory, and it's just some rubbish. It's going to get deleted when the computer reboots. And so now that we've got our data directory and our temporary directory ready, let's take a look at how we would read files. So let's start really basic. So let's just look at our temp directory. It's empty. And let's just write a list of integers to a file that we called a.dat. And we're going to put that in our temporary directory. So first we would get our file path. And here's our data that we want to write. So now I can just say write file path and then the data itself. And it will tell you how many bytes have been written. Cool. You can even look. There's actually a file called a.dat. And now let's read it. So you might be tempted to say, well, I'm going to read the file path and I want to read integers out of it. But this is a really low-level operation that we were doing here. So we just read a integer out of the file. That's all. So the problem is that read doesn't know when to stop. I could put in another data type, like a string, and it would interpret our list of integers as a string and whatever encoding is used on this machine. And you can actually see our data here. We've got 0, so we've got 4 in binary. So these slashes are binary. We've got a binary 2 here and a binary 3 here. All right, so how would I get if I know what the format of the file is, how would I get the data out of it? And so here is our little snippet. I did warn you that the do block will reappear. So let's walk through this carefully. The open function takes a path, and well, it actually takes 3 things. It has 3 input variables. The first one is obscured by the do block. So the second argument is path, and then we tell it in what mode to open the file with, this time in read mode. And then the first argument, we give it a function of what to actually do to the file. So the function is actually in this do block. So IO is going to be the thing that is going to be the beginning of our anonymous function call. And so it's going to get given a file handle essentially. And so while we're not at the end of the file described by IO, in this case, you could just have a vector and we push. I realized I haven't done push and pop. You can, if you just want to add to a vector, there's a function called push with an exclamation mark, and that just adds to the end of the vector. So we could push here, but in this case I'm actually printing. So while we're not at the end of the file, what we do is we read an integer, and we print a comma as well. And now we've got our file content displayed here. So this is also how Julia ensures that the file gets closed, because the open function, it applies our function that we've given it, and then it closes the file again. All right, so this was really low level. Oh, by the way, I wanted to mention, we are reading binary data out of this. So this file wasn't a text file that contained the ASCII representations of 423, but it actually contained the binary values of our data. I encourage you, if you really have a lot of temporary data that's huge, use an efficient file format like binary data. All right, the other thing that you'll probably encounter loads is the JSON format. There is a helpful package called json.jl, so we're going to be using that. And json.jl will map dictionary objects in Julia to JSON files. So for example, I can create a dictionary object that, it's really key value pairs, right? The A string is 1, the B string is the string hello. And that can be encoded in JSON. So if I just ran JSON of my dict, I would get a string representation of my JSON back. So it's just a string. So if you wanted to write that, I would just open a temporary file called d.json. And then I give to the write command the path and the JSON encoded string. So the JSON package actually didn't do any I/O in this example. So and if we can actually go the other way around, we can read the JSON file. We have to read it as a string, and then we can use json.parse to turn it back into a dictionary. Later we'll see some neat little tricks you can do around just streamlining some of this. And then finally, we probably want to also store tabular data. Data frames at the moment, dataframes.jl at the moment isn't really good at storing data. Last time I checked, most of the solutions revolved around taking the data frame and coding it as CSV and then storing it. So this is what we're going to be doing here. So I'm going to use a data frame and a CSV file. And so CSV and data frames are great for tabular information, and at least in my opinion. So let's create a table. This is really a silly little example here. The table will have 3 headers: the name, the age, and how many coffees you've had. And you can see the data frame object, just like in pandas, has a different data type for each column. Columns can contain missing data, by the way, just FYI. And so I can just add to a data frame. This is something that I really like about Julia. You can quite efficiently do row by row in data frames. So I can just add the following list of information. So my name, my age, and how many coffees I've had. So you can just use the push command as if it were a vector. And I can also add someone else. And now we might want to save that to disk. That's pretty easy. We can use the csv.write. So this is no longer the Julia write command, but the write from the CSV package. And we write to the coffee.csv. And CSV is capable of understanding the data frame format. The csv.write doesn't tell you how many bytes it's written. It actually tells you where the file is saved. And so we can see the file has now appeared on our disk. Oops. And we can even just look at the content using our cheap print each line. So now we are doing a slightly more advanced iteration. Rather than iterating over each character, we're going to iterate over each line in our file, and that's what readlines does. And then we can print each line. And you can see this is a typical CSV format. And if I wanted to load the file from disk, what I have to do is I can just give it a pointer to a file, and this will just create a representation of the file content by having CSV rows. This isn't very helpful for working with data, so it's really helpful to just send that straight to a data frame. And so here we see the next thing that I really like about for data analysis, and it's the piping operator. And so I could just write here data frame of CSV file, yada, yada, yada. But rather, I can also say, well, take the output from my CSV file and send it straight to my data frame constructor. And that gives me a data frame again. So data frames is actually intended to be pretty powerful. If you wanted to manipulate very large tables, this is what I recommend. And so let's read this CSV file. It contains a bunch of COVID statistics. Yeah. So the question, right. So the question is piping, it's essentially asking if it's syntactic sugar, right? Is it replacing, is pipe, is this thing here just creating a for loop and then reading each row and then pushing to the data frame the content of that row? That's the question. It's a very good question. I think not. It probably, when compiled, it's the same kind of code, right? It's a loop. It has to iterate over a data source. But under the hood, I mentioned asynchronous programming. I don't actually know if this is implemented this way. Probably a Julia developer looking at this later will scream at me. But if I were designing this, I would create a data channel. There's channel objects. And my receiving function will take data out of the channel and bit by bit. And the reason why that might be better is it won't load the whole file into memory once and then duplicate it in memory and then delete the original file. Rather, it takes a chunk, processes that chunk, deletes the original chunk and moves on, and it's much more efficient that way. In many languages, the read operation or the read lines is implemented in a similar way, but beware. I think in some cases I've actually run afoul where the read lines operation actually read the whole file into a vector. So this also depends on how the data frames package is developed. I have a lot of confidence in the data frames developers, so I'm pretty sure that this is how they're doing it. But maybe take a big data set and profile memory usage while you're reading it as a data frame. All right. So here's an example, and it feeds into an example notebook in this repository that y'all can experiment with. Just making sure, yeah. And so if you've got a big file, then once again, you can open a CSV file. This is a couple of megabytes of CSV. And if you just took this data frame, it's actually it's imperfect data. So here is a fairly useful tool if you're doing your first exploration. You might later come up with functions to fix missing data, but often drop missing will just drop all the rows that contain missing data. And so then you get this giant table. It scrolls down off the screen here. And so we can use describe to get us a high-level overview. And actually, you'll see this when you have very long column names. In Jupyter, the describe and the print functions will omit columns, which can be pretty sneaky. So at least it won't omit any rows here, unless really it could. So the point is, if you just rely on the print function, if you just rely on calling this function, then you're going to miss data. So way to, if you see omitted columns or rows, you would just save this as a data frame and then iterate over the data frame manually. And so this is another helpful tool for working with data frames. Let's say we wanted this many confirmed, we wanted this column. Then the idea is you take the text verbatim and you use that to index into the data frame. So this is a data frame object. We want to take all of the rows, and so we're basically taking a slice, and this will actually then return a vector. So this is a really common workflow. Is you've got some data types, so some data that you want to slice out of a data frame. So that's what you do, and then you get vectors out of that, and then you can manipulate the vectors like normal vectors. And then finally, maybe we only care about the COVID data that refers to the US. So in the previous example, we were slicing over all the columns. Now what we're going to do is we're going to do the same, but our slice is now a Boolean operator. What we do is we look at our data. Oops, excuse me. We basically, this here gives us a vector of all the country codes in order. And then we do a broadcast equality check on the string, and the country code for the USA is USA help. It's very helpful. And so then we can use that vector of Booleans, right? They're going to be true or false for each row, depending on whether or not the country code was equal to USA. And we use that to index over rows, and then we extract all the data. We extract the subset that refers to the US. Sure. Precisely, yes. So the question was, if I drop the broadcast, would it just create an error? Yeah, it would say, well, and once again, that can be sneaky, because like in the case of comparing a vector to a string, no, it's not going to accidentally say, well, if I have a string of characters and a vector of characters, isn't that also a string? Right, like it won't do that. So if I took a char string, so a char array, and then compared it to a string, it would also tell you, now I can't compare those two. But sometimes you can get into trouble. So it's worth thinking carefully about what you're broadcasting. All right. So I mentioned that files are usually a good starting point, but maybe we want to actually do something more advanced. And so I want to show you this example of interfacing with databases. There's also a similar approach of interfacing with APIs, so REST APIs, for example, and message queues, but they follow roughly the same pattern. So this is, I think, just going to get you started on that to help you think about future projects. So this is an example exercise that's a little bit less depressing than COVID. At one point, I decided to collect all sorts of power usage data from my fridge. And so the examples live in this directory, but not the data. The data is in a database, because I was reading a e-meter at a frequency of about once a second. And so I didn't want to just have a file that I increment every once a second, and then like some process gets jammed and maybe two processes talk to the file at the same time. No, that's a job for a database. So by the way, the data is time data, so it's really helpful to use the time zones package. And here's an example of the sort of shenanigans you sometimes have to do. This will convert a timestamp to your current time zone, right? So basically, I will take the timestamp, the Unix timestamp from the time zone GMT, and then I'm going to send it to the target time zone, which in this case is America, LA. You might notice this notation. I'm declaring, first of all, I have got a semicolon here, and then I am doing this sort of a Python-style function definition. This is an optional variable. So everything after a semicolon is an optional variable, and whatever comes after the equal sign is the default. And so this is how you would read the fridge database. This will depend on your exact table schema, and so I just chose something that is designed to be, sufficiently complex to not be trivial, but it's also not very difficult. So I am going to create, in SQL speak, these are variables, v1, v2. And this bit here, this db interface.prepare and then execute. This is how the MySQL Julia package talks to databases. This is actually not a very good design. The idea is that if you're running a SQL command over and over again, then MySQL.jl breaks it up into a preparation step and an execution step. So if I have the same step over and over, I can prepare it once and run it multiple times. And that saves me on a whole lot of overhead. Let's unpack this carefully. What I'm doing is I'm selecting from the emeter start table. So I'm selecting the field emeter start from a table that I call name, where the ID, IDX, is equal to some value. So that basically just looks up this value, emeter start, wherever this ID is equal to IDX, and then stores that in V1. I do the same thing with V2, except V2 is now emeter end. And then finally, I select everything from a table with the same name underscore emeter, where IDX is between V1 and V2. So essentially, this is a really common schema. I have a table that stores some indices, start and end indices. That's what the table name is for. I look up those indices for whichever event that has ID, that has an ID. And then I go to another table and I look up all the rows that are between those two start and ends. And then I return all the data. And so these two execute commands will just set those variables in that database instance. And then I get the events out of the database by just looking up that data and then piping that straight to a data frame. So you can see a lot has happened here in just this one call, right? So this is just a standard way of how we would interface with one particular database. And then, of course, at the same time, we might want to also transform our timestamps from the whatever timestamp is in the database to our current time zone. And we might also want to turn Unix time, which is not that helpful, into a human readable time format. And that's what this timestamp function, we defined that here, does. All right, so a lot going on. Let's see that in action. But before we do that, this is a little helpful trick. It's not super secure, so don't let your database admin see this. But we want to have a place to store our database credentials. And I've decided to make this a little bit more of a complicated class type. Okay, so this is a struct that you all know now. Mutable is a statement that we add if we want to have a struct that someone can change. So maybe I want to override the host IP address. So that's why I make it mutable. And kwdef puts an automatic default constructor that can take any dictionary and map it, as long as it has the same format, to our our class. You can probably see where this is going. Here we go. This is really when people who use Julia want to show off. And a lot of code looks like this, so it can be really dense and hard to understand. But let's see what happens here. Let's start from the inside and go outside. We start with a JSON file that probably holds our database credentials. We parse that using the json.parsefile function. Now, that would give us a dictionary that matches string field names with values. That's not very helpful. What we want is we want those values to automatically land into these fields of our struct. I'm basically lazy. I don't want to put quotation marks everywhere. That's what's happening here. Well, I can tell parsefile not to just take a dictionary and give me string fields. I can say symbol fields. This is something a little strange maybe, but basically the idea is every time I see a string for a field name and it has no spaces in it or illegal symbols, it can automatically be turned into what's called a symbol type. Now, once we've got that dictionary, it's this bit here, we unpack it, like so, and then we pass it as literally arguments, named arguments, to our database credentials kwdef struct, which is this guy here. Yeah, lot to unpack, I'm sorry. The reason why we do stuff like that is because often we want to keep that, that struct somewhere in memory where we know it's safe. And then later we can use it like so, right? We've got, we can have the credentials, host, username. If DB interface actually allowed for named arguments, which the developers haven't implemented yet, then we could just pass our struct straight to it, but fortunately not. And so in this case, we have now established a database connection. By the way, the credentials that are in the GitHub repo will get you access to this database. It is a super, super cheap micro instance in the cloud. So, you know, y'all can go and experiment with that. You have read-only access. But if it's a bit slow, it's because it's just little tiny, like the cheapest one that I could find. We also have the NERSC credentials for a NERSC database, but our, well, I'm having performance issues that I didn't have time to fix yet. So I think there's a problem with that one. If you're accessing the NERSC database, it should be much faster. Anyway, so let's look at some data. I have a silly sense of humor, so of course I called my database Atotska Ministry of Energy. If you know the game Papers, Please, you know the reference. Now, our database, I know, has a bunch of indices. They go up to 61, I just know this. I know I've created these indices for debugging, and this was something else. And so I am just going to create a list of data frames. So that's what this square bracket here does. It creates a vector of data frame types. I said that we shouldn't do this sort of stuff, but I'm cheating here, and it's only temporary. And so then I will go and iterate over all the indices between 1 and the maximum index, and I will push to all eMetadata just the returned data frame from that particular database query. And after that runs, it takes about 5 minutes. It has grabbed a whole lot of data. And so if you just looked at all eMetadata, you just get this vector of data frames. That's not very helpful. So what we're going to do is we're going to concatenate all of these data frames. And that's what the vcat command here does. I could have done that in the for loop, I know, but I just wanted to demonstrate that I can take a vector of data frames, and I can vcat them all together. Now you might have noticed this ellipsis operator. That just says, take this vector and pass it as a list of arguments to vcat. And so now I have a fairly big table. It should show, oh, okay, I don't know, later we'll see how many entries, but you can see that I have a bunch of indices. These are Unix timestamps, milliamps, millivolts, milliwatts, and watt hours. And we can have, min, max, all of these properties. And so next, what we want to do is we want to take this data and we can actually look at it. So this ends the I/O section and starts the exploring the data section. So before we start plotting and exploring the data, I wanted to just do a very, very quick aside about plotting. Yeah, sure. Mm-hmm. Mm-hmm. There is distributed data frames. I can look up the repo later. It's pretty neat, actually. So you would probably, by the way, the question was, what if the data is too big to fit into memory? Well, what you would do is you would use distributed, and then each worker would access, hopefully also a distributed database, and would query different ranges within that database. And then you would put that in a distributed data frame, and distributed data frames allows you to, I think it's just called distributed data. I will have to look it up. That will be just like distributed arrays. It allows you to synchronize, so it allows you to remotely fetch indices that aren't local to you. And then it also allows you to work locally. So that's it. Did you mention Dask? Yeah, it's very similar. I think it's pretty much they're copying Dask for that. Yeah. All right. This is a really very, very simple example of how to use plots. First of all, it's called plots. So just using plots, I can create just some really silly data here. And remember, I'm broadcasting my mathematical operation here, so I'm not doing a matrix multiply with two vectors that are of the same shape. And so, oops, let me just fix the format. And so, for example, you could plot a parabola if you just use the command plot xy. Now, y1 is a parabola, y2 is a cubic function. What if I want to plot two things on the same axes? Remember I mentioned earlier, if I put an exclamation point, the idea is it sort of mutates something. So there's a function called plot exclamation point. And that will not clear the previous plot. And so if you just ran plot without the exclamation mark, it would override the parabola with the cubic line, but instead now it just adds it to the same plot. So another thing that you would probably want to do is curve fitting. Here's some basic noise added to a linear function. So here's my linear function, and I'm adding 2 times rand, and I'm giving the length of the vector x to the rand, and then it's basically a uniform random variable with 0 mean and width of plus or minus 1. And so if I plotted this, here you can see a much more advanced version of plotting. Remember, the second plot adds the first plot because of the exclamation mark. And so I might want to plot the data, the x data pairs, but I don't want to connect them to a line with a line, so I'll say line equals nothing. The marker is, and this is what I meant with symbols. If you have a colon and then just some string, that's called a symbol. lazy person's string, basically. We want to move the legend to the top left, and we want to call it noise. For the second one, for the second line, we want it to be solid. We want it to be a bit thicker so it stands out from the circles, and the label is called original. and so then you get a plot like this. So now let's fit. There are many ways of fitting, and so I'm just going to demonstrate least squares. I mentioned the @dot operator for broadcasting. So here it is actually in action, right? So this model, it takes data and parameters. And so the data is going to be a vector. And yes, the data is a vector, and the parameters is a vector as well. And so I'm just specifying my model function this way. And so then I can use from least squares, I can use the curve fit command to fit the model to the data, and I'm giving it an initial guess of 0, 0, and it will create a fit object where fit.param is that parameter vector. And so if we actually plotted now the fitted parameter on the same plot, you can see it agrees almost perfectly. All right, so this is what we're going to need for the next section, where we actually want to look at some of the statistics. So these are the statistics from the fridge. First, I wanted to just briefly address piping again. This is a frequent hack that I use. The filter and the map function, for example, exists to, they kind of describe what the name describes what they do. So map, for example, will apply a function to every element of a collection, and filter will take all the elements where the function returns true. However, I might want to chain them. And so what I do is I define, first I have to import those from base, and then I define a version of filter that takes a function variable only. And what the function does is what this does is it returns a function that takes data and applies f using filter, and we can do the same with map. And this is helpful because let's make some basic data here, just 0 to 10. And so I might want to now pipe that data through this map to produce a augmented data. In this case, I'm just adding 1 to the data. But it's nice because now I can start chaining these things. I can map, and I can filter in one line. So now I'm only returning, in this case, it's a bit silly, but it only returns even numbers. You can actually do one better. There's a package called chain that lets you do this in one nice little block. So you just use the chain macro, you give it the input data, and then you just list each line, each individual step, and you use a underscore to represent the output from the previous line. So you can imagine you might have a data set, and you might have several data preparation steps. You might want to drop faulty data, you might want to do some correction, you might want to do some sanity checking. And so this is what chain is really used for, and you can kind of do that in one quick pipeline. Sorry? The sign? Oh. Oh, how would I say, like, now give me that result? So if I went, for example, y equals @chain x do, y would then have the value, the result that is these numbers. All right, let's remember we looked at our huge function to extract all the data. we have all the e-meter data. And let's have a look at how much data we've got here. All right. Right, so we have 4 million, basically 5 million lines of data. They contain this milliamp, millivolt, milliwatt, and so on, and some timestamp. The timestamp just is mainly there to help me debug things. Now, I might not want to analyze all of this data. Remember, this is 5 million lines. Oops. Hey, I thought I had it. There we go. This is 5 million lines. I don't want to analyze it at once. But I also don't want to make a little copy of a chunk somewhere, because that's also going to waste memory. So what I'm going to do is I'm going to create a view into this data. I'm going to say, with add view, I take my array and I'm going to go 200,000 entries back from the end. I'm going to give me the last 200,000 entries. I'm going to take every column, so then I get this kind of table. And so I might just say, well, let's just plot the voltage that this thing is measured. By the way, you might wonder, well, plot, can that do data frames? Well, this statement here has already converted it to a vector. Remember, if I index using the colon, I return a vector. So I'm in a slice using a colon, I return a vector. You can actually slice with an exclamation point, and then you return a data frame. So yeah, this is a plot of, and it's basically the voltage fluctuations on the electrical grid. So that's kind of neat. So next step might be, well, what does this look like? So the basic way of taking a histogram of a data set like this would be, I'm going to take, as I said, a view of my e-meter data. Actually, now I'm taking a histogram of everything. I'm sorry. I'm going to take a view of my e-meter data, and I'm going to use from stat space, I'm going to use the fit function, and it will fit a histogram. It's a little bit weird, I know. It will fit a histogram to my view into the data, which is called T here. And I'm going to go in bin steps that go in units of 8 over the maximum of whatever value is in my voltage, in my millivolt. Right, so I'm going in steps of 8 millivolts. And then I'm going to use from linear algebra the normalize function that will normalize my histogram, and I'm going to use density mode because I want it to be a probability density function. Right, so there's a little bit to unpack here, but essentially I'm fitting a histogram to our data, and I want it to be renormalized so that the area under the curve is 1. And it actually would return a histogram object. Right, so the way that histogram objects work is they actually have the edges of the bins, which if you wanted to plot it as a line, you would have to convert that to you would just have to take the midpoints of those bins. And I can do that with these 2 lines here. It's a little bit weird, but basically edges is a range. So I'm going to have to collect it to turn it into a vector. Okay, that's straightforward. And then what I do is I start at my edges at 1. I go not to the second to last edge, and I just add the difference between the 2 adjacent bins using the diff command. So that gives me the midpoints of my values. And I can take the weights, and I can plot this, and I've actually dropped all the negative count, so all the 0 counts. Anyway, so then I would get a histogram like that. Now this is a little bit much work, really. So instead, what we do is we can cheat a little bit, and there is a function I really like called average shifted histograms, and that just does it in one fell swoop. It uses a version of kernel density estimators to create so you just give it remember T is just the raw voltage data, and then I can just plot that straight away, and I get a density curve and a histogram out of it automatically. All right. There are some more detailed examples that we can look at later, but I wanted to make sure that we have time to also cover some machine learning and automatic differentiation, because I think that's an area where Julia really shines. And so we can it's almost, yeah, we can leverage the way that data types work in Julia to implement our own version of automatic differentiation. There's a package called Zygote that does this properly, but this is really for illustrative purposes. So there's an algorithm called the Babylonian algorithm. It's really just Newton iteration to solve for the square root of 2. And so it really takes the value t, and then you've got x over t divided by 2, and that gets put back into t, and that will eventually give you the square root of x. We can just implement that in this version. And then we want to check that the square root of 100 is really 10. Yep, after 10 iterations, we've actually already converged to 100, so that's nice. And we can look at the square root of 2 and compare against the true value, and yes, it's a pretty good estimate. We can plot the convergence behavior of this, and you can see it starts off as a linear function and eventually converges to the square root function. So now we can use automatic differentiation to create to find the derivative without actually having to do anything like finite differences. So the idea is to introduce a dual type. So the dual type is a kind of a number. It actually contains a tuple, so it contains it's a pair. It's the original number and the gradient of the slope at that point. And at the same time, we're going to tell Julia what the rules for what the product and the quotient rule are. The reason why we only need to do that is because if you look at the original algorithm, you know, we basically have we have sums and we have quotients. Do we even have products? Don't think we need the product rule even, but nevertheless. So we define the product and the quotient rule, and of course we have to define sums and differences. And so this is what we do, right? It's straightforward. You've seen this before. We import all the operators that we need. We define the rules. So this is plus and minus. It's straightforward. You will notice the product rule here. You'll notice the quotient rule down here. And then we do the typical kind of conversion and promotion. The first thing is when we start off a dual number, we set it to 0. We set the gradient to 0 for a scalar. It's a bit of a hack, but this is what we need to do to make it work. And whenever a dual is involved with any other number, out automatically comes a dual. This is what all the automatic differentiation packages like AutoGrad and PyTorch do in the background. And so we can just say, what is the gradient at the point x equals 25? So what we want to know the gradient of the squared function around the square root of 25. So we start with this tuple here, so 25 and 1. And then we run it through the Babylonian algorithm. And but before we run the Babylonian algorithm, what we expect is 5, right? The square root of 25 is 5. And the gradient at that point is 0.1. and the Babylonian algorithm, without changing the algorithm, returns the same result. So I think in order to fully appreciate this, the point is we didn't touch the original code, right? So the Babylonian algorithm is a stand-in for any kind of code. As long as we're not going through an if statement that introduces some sort of discontinuity, we can now use this to differentiate any algorithm. And so, and the reason why this is neat is because it means that packages like Flux can differentiate any loss function, not just the ones that you express using Flux data types. All right. So let's look at a basic example using FluxML. So Flux is basically the PyTorch of Julia. I want to recommend the Talk Julia podcast. They basically had this example, and they have a really nice video walking through it. So what you're going to do is you're going to install Flux, and then you have to prepare the training data. Now, it's a little bit different to packages like PyTorch, and we'll see in a second, but this example is really, really simple. It really just is illustrative, and we can look at something more sophisticated later. However, let's say we want to get a neuron to learn the linear function. So we start off, we generate a training in a test set, and we do like a 5-4 split. Sorry, 6-4 split. Just to illustrate, like the training set is kind of trivial. Yeah, we know that. And now we're going to look at the single neuron model. Well, it's pretty straightforward. It really is just a linear mapping from the inputs. So the activation function for this model is really, really simple. And we can express that in Flux using the flux.dense model, right? So number of inputs and number of outputs is so the way you define these is you have to think of in terms of layers. So you have a single input layer with a single output, which basically means we've got one weight and one bias. And we can even look at the internals of these models by using the dot weight and dot bias fields of this structure. Now, just like PyTorch, we overload the call operator. So even though model is a struct, there is a call operator for the struct. So I can just, for example, pass in a vector and of the training data, and I get out a vector of the prediction. Well, we all know what the mean squared error function is. So Flux has a submodule called losses, and this defines for example, the mean squared error. And so we could just, for example, plot the loss. Well, right now it's a meaningless number. And of course, we're going to look at gradient descent using the Adam optimizer. So what we do is we create a optimizer object called descent. And in order to train, we need to keep track of the parameters that our model uses, right? So you use the flux.params function call, you give it the model, and it then tags all the weights and biases using these dual numbers that they use zygote. They don't re-implement dual numbers that way, but use zygote to build these parameters that it's going to be used for training. And something that is slightly different to what you might know from PyTorch is that the data is actually a single vector of tuples, where you have input output for each tuple, right? So in PyTorch you would have an x and a y vector. In Flux you have a single vector of tuples. All right. So you can use the train function, and train mutates the state, and therefore it's got an exclamation point. But basically, you just call the flux.train method, and that will do in this case, a gradient descent step, right? So it takes the optimizer and the parameters, and then it will create mutated parameters that, in this case, because it was completely untrained before, have significantly decreased the loss. And unfortunately, this is just an aside, if you just took descent from Flux, it produces, so it uses a full gradient descent. So if you wanted to do something like stochastic gradient descent, you would implement it using this sort of batching model here, where you do a single point, you put in a single datum to the full gradient descent, and this way you create stochastic gradient descent. And if you ran this, in this case for 1,000 epochs, you produce incredibly low loss. In this case, because, well, we're literally just fitting the gradient of our model, we wouldn't expect anything else. We could plot the losses here, and this is exactly what we would expect. So just some, and then of course, now that we've trained our model, well, it's an illustrative example. All right. I want to look at at a more sophisticated example. Ooh, I have that in the examples directory. Ooh, I'm sorry, I skipped something. I also wanted to look at interactive data exploration. Right now at NERSC it's not working, so what I really recommend is that you try the Pluto package. And when you start Pluto, this is way too small. When you start Pluto, you will see something like this. Now Pluto is like Jupyter, but the idea is it's sort of stateless. So when you change one cell, all the cells that depend on it get reevaluated and automatically updated. So here we have our fridge example again, but now I'm not looking at all the fridge data, but this one particular, I actually used the same sensor to charge a battery, and I just wanted to see what that looks like. So that's what this here is. Now, here we're seeing the current draw over time. So it's sort of maxing out, and eventually it exponentially decays. And let's imagine I want to fit a model to this, but I'm just not having any luck with my fitting algorithm. So maybe I want to explore some things and check out the parameter space just to see how the dependencies are, maybe limit some of the inputs to my model. And so that's where I am really sorry, I have to actually zoom out a little bit, otherwise we won't see anything. That's where Pluto is really helpful. And Pluto has this idea of binding sliders to the Pluto notebook. So that gives you these little sliders here that you can see. I can just set them to arbitrary values, and it will automatically update this notebook. So you can, for example, see, okay, this is the effect of this slider. I'm about to run out of battery, excuse me. And so I recommend that you experiment with these settings here, and you can kind of see like what values might be a reasonable ansatz for some sort of fitting or optimization problem. Okay, now that I'm sorry, I mean, this is also part of the repository, so I recommend you have a look. Unfortunately, you can't run this at NERSC at the moment. If I can find my slides again. All right. Okay, so I wanted to talk about a more interesting application of flux. And I have it somewhere. Here we go. So now I'm on Perlmutter. And so in the exercises folder, we have a recurrent neural network example. This is an example that's based off another blogger that I follow, Jonathan Chesot, I think is how you pronounce his name. It does need some updating because flux likes to change. And so sometimes you'll find an old example that doesn't work particularly well. And so my recommendation then is to look carefully at the error messages, and it's usually a very small change that you have to make, but it can be annoying. But in this example, you see pretty much the same elements that you've seen already. You have, we're going to read this CSV file. This is the Apple stock price. And we're going to build a recurrent neural network to predict the stock price of the Apple stock. Now, this is a very naive way how you would build a recurrent neural network. At the end, I'm going to suggest maybe some changes, but let's just start with the naive way to illustrate how we might train this thing. So the first thing is we have this list of prices, and we want to use today's price to predict tomorrow's price. You might think, actually, maybe we want to have a little sliding window. But for this example, let's start with today's price. So my X values and my Y values for the training set are just going to be the shifted data, right? So I'm going to have to, so the first element of X corresponds to the second element, the future value for Y. Now, remember, what we need are tuples of X, Y values for our training, but also, now this is something that refers to the way that the recurrent neural network module is implemented. The recurrent neural net expects a vector input that is of length the number of features that you're looking at. So in our case, we're just looking at the previous day, at today's price. So in this case, what we want is a feature set of length 1. And there's several ways to do this, but this isn't a half bad solution. So we're going to create a for loop, and you might not have seen this notation before. You're going to, maybe I can just demonstrate this here. I can type /in, push tab, and it turns into an element symbol. But it's the same as if I had written in at that point. So I'm going to iterate over all the elements in my training set in the X set, and I'm just going to turn them into an individual vector of size 1. By the way, this is another thing that you might have noticed. I can broadcast the float32 constructor, and that way I would cast my data from double to single precision. That's really common if you want to do machine learning. Normally you care only about single precision. And now we want to build our model. And so the model that we're going to look at, this is sort of a simplified one. I would probably use a LSTM, but this is a simplified version. We're going to take a recurrent neural net. It takes one feature. It outputs 32. Those are then going to be fed into 32 inputs of a dense layer, and it will just predict one quantity, which is the future stock price. And we're using the ReLU activation function, and if we pass identity, we're just saying the activation function is just the identity function. And you can use the flux chain function to chain together layers. So you don't have to wire them up yourself. It happens behind the scenes, and you can kind of see what Flux does. It uses this recur wrapper to deal with all the recurrent mechanisms of a recurrent neural network, and then it passes that to dense. Normally what you would do is you would create a loss function that warms up your recurrent neural network. And one way to do this is just to take the first input, you just pass it to the model. Remember, it's a recurrent neural network, so it stores state. And you just ignore that result, right? So this is sort of like a warm-up step, and then for every subsequent call, you compute the mean square error loss for our model. But I thought actually in this example, it's kind of neat. Basically, everything in here is being done by the flux.train function. I've had issues getting this thing to work in later versions of Julia, so I don't know what's going on there. But this pretty much shows you how the train works using the full gradient descent. We basically create a gradient object out of our parameters. We pass the loss function to that gradient constructor using a do block, and then we update our model based on gradient descent using this optimizer opt here. And so if we were to run this, you would see this thing to count down. We see that our loss sort of just, it converges to something. I was just playing around there. And this is how our model performs. So the model seems to do terribly for past stock prices, but then after some time, let me maybe zoom, yeah, after a brief moment, it starts to like the recurrent neural network essentially starts to learn the historical price of the Apple stock. All right. And the other thing that I wanted to show, so I wanted to make sure that we've covered at least a little bit of Flux. By the way, you might be wondering how do I run this on a GPU? In theory, the way you would do that is you would make sure that the training data and the parameter data is stored as GPU data types, and then you just pass it to Flux, and it just works. I couldn't get it to work for the recurrent neural network though, so you know, there might be some fiddling involved. Right. I'm trying to find. Okay. Any questions so far? Yeah. So we're approaching the end. I just wanted to maybe recap this fridge example a little bit more. Now this is the beginning you saw, but maybe you were wondering what the data looks like, and also I can't zoom in that far, and also I wanted to demonstrate that by by being able to leverage a just-in-time compiled language, it allows us to do what I consider a much more natural way to actually experiment and analyze features from data sets. So let's just think about this example again, the last 200,000 entries of the fridge data set. But this time we are going to be looking at the milliampere reading on our e-meter. So basically, the way the electricity grid works is that the voltage, it does fluctuate, but the grid controllers try to keep it constant, as constant as possible all the time. So if you want to know what a device is doing, it's helpful to look at the current it draws or the wattage it draws. And so I was looking at the milliampere data. And so this is the kind of data set that you can get out of it. And so it's not necessarily something that you can immediately throw at a neural network to analyze, or maybe you can do an FFT, but you also maybe want to experiment with like the taxonomy of a data set like this. So the first, so this is the power, excuse me, I'm sorry. Here we go. I was doing some validation steps. So the first thing that you wanted to do after you've sort of validated things, one validation I do, maybe that's worth pointing out, is this is cheap equipment. So let's compare milliwatts with millivolts times milliampere divided by 1,000. Those two numbers should agree. And they sort of kind of agree, but there's a bit of a difference as well. So that's basically what happens when you buy cheap equipment. So either milliwatts or millivolts are, so milliampere are helpful, but maybe don't take the exact value at face value. Maybe what's more helpful is just the pattern. And so the first thing that you might want to do is you might want to look at one of these spikes. And so what you see here is an initial spike and then some constant usage and then no drawing here. So you already know what's happening here. The fridge draws almost no electricity until the compressor jumps on. It seems to create a bit of a spike, and perhaps it's a bit unusual. You get a pretty high spike. Maybe that's just our measuring equipment just going insane. So maybe you want to do some smoothing here, but the point is we have some initial spike, the compressor runs, and then it shuts down again. I mentioned, milliwatts and milliampere times millivolt disagree. Excuse me, as you can see, and you can look at you can keep looking at these spikes, and this is something that I found out that is kind of neat. All right, so this is the compressor turning on. Here's some data artifact which we might have to filter out. What's this? That's the light turning on. So basically, at this point, someone got some salami out of the fridge or something. So this is the other kind of data. And so, as I said, you do want to experiment with this data a little bit, because if you just took a histogram, you would see things like this, right? This is the histogram of the same time series here, and you see individual spikes here that correspond to different peak heights, essentially. So you can see that you have many small peaks, and then you have, with increasing current being drawn, distribution of peaks. So, sorry, as I said, I was actually playing with this data a little bit, so there's some scrolling involved. So what you want to do at this point is, I want to be able to identify the peaks. And so I mentioned earlier, the peaks usually follow the same kind of pattern, right? You have a rising edge and you have a falling edge, and you have some sort of excursions usually involved with a rising edge. At the same time, the plateau, the maximum value of the rising edge, can have different discrete values. And so our algorithm will probably be a rising edge detection algorithm that tries to somehow compensate for excursions. And so this is the version that I was able to come up with. It starts by looking at the previous value is it below a threshold, and is the next value above a threshold? That means the rising edge has crossed the threshold. And we invert this logic for the falling edge. Then we want to do a excursion detection. And so the way you detect an excursion is you look for a rising edge and a falling edge happening at the same time, right? It means that within 2 time steps you've risen and then you've fallen. This works because you're going to -1 index and +1 index over here, by the way. And so if you have an excursion, you want to somehow eliminate that. So that's what this function here does. It finds all the excursions, and for every excursion it finds, it takes that excursion value and just replaces the average. All right, so the idea of this algorithm is then you take your rising and your falling edge detection logic, you compute the values of the rising and falling edge, and you basically keep track of these pairs of rising and falling. If that works out, you basically, well, also you patch the excursions first, but you basically run this here, and that's how, I basically found during that time about 2,000, almost 2,700 peaks in the fridge data. By the way, these thresholds were informed from just those histograms. So you can see there's a lot of fiddling here involved, but I think that's also the objective of our hands-on style of analysis. And so what we want to do now is let's take a plot of all the peak data between the rising and the falling edge. And you probably also, what you also want to do is you want to eliminate very small fluctuations, and you want to plot a little bit before the rising edge and a little bit after, just to see that you can resolve the edge. And so that's really what we have in the data. You have a lot of different kinds of peaks. And I think this is kind of fascinating if we, right. So if we take all the peaks, including the times that we open the fridge door, we get this kind of mess. Let's ignore the times we open the fridge door, and we see this kind of data. And so this is already the starting point, I think, where further analysis can go, because now you see what's happening here. You really have 2 kinds of duty cycles in the fridge. You have one that seems to have a plateau that's roughly half of the second duty cycle, and the length of the duty cycle will depend on some other parameter, right? There's definitely a distribution here, but it's pretty broad. You might ask, well, is it maybe the ambient temperature? Who knows? And by the way, the second duty cycle up here, that's the freezer compartment, I think, at least in terms of the timing. Anyway, so this, I think, do I have, oh no, this is just the voltage fluctuations. So yeah, this was supposed to illustrate how you would dissect a fairly large data set using Julia. Maybe one of the takeaway messages that I want to encourage everyone to think here is, if you've been working with Python and you've been thinking, well, I shouldn't have a for loop and an if statement, that's allowed again. And I think that allows you to build maybe a little bit more intuitive algorithms than having to think about, well, how would I do this in NumPy? All right, so I think that I think we've actually covered all the material that I wanted to cover. Wow. There's a similar example with COVID data, which I think is a bit depressing. And so I think I will leave it at this and encourage people to ask questions. And if you're on Zoom, unmute and you can also ask questions there. This is a question where I have to stop being opinionated. Yeah. Okay, so the question was for someone who uses pandas, PyTorch, basically the Python data analysis stack all the time. Would my recommendation be to switch, or maybe also under what circumstances to switch? I always think that if you're developing things that require some sort of custom expressions, so for the fridge example, it is being able to implement this edge detection. Stuff like that is not trivial in pandas. You can do it, I know, and I've done it with, but you have to always think about shifting, and what if the edge, this time the edge is really, really sharp? What if the edges aren't so sharp? Basically, you should ask yourself, is there a library that already does what I need it to do, and do I expect this library to continue to fulfill my production needs in the future? If that is the case, I don't think you need, probably you shouldn't invest time in completely retooling your pipeline. However, if you want to do some more experimental work or work that hasn't been implemented in the standard Python framework, or if you want to take this kind of data analysis and now do it at scale, and you haven't yet written your Python code at scale, then I suggest you switch to Julia. I also can give maybe a slightly different example. One of the things that I'm developing in with Flux is with a student, we are working on trying to use neural networks to tune the parameters in linear solvers. So ideally what I want is a loss function that's maybe 10 iterative steps of a solver, right? However, you can't do that in PyTorch, right? You can't just say, well, here is a GMRes implementation, run this 10 times, that's your loss function. The input parameters are the parameters for GMRes. But you can do that in Julia. It's hard. And the reason why I'm not showing it to you here is because it doesn't work very well at the moment. But it's more possible than doing it in PyTorch. And this was actually one of the reasons why that part of, that was a situation where I'd actually taken a PyTorch pipeline and re-implemented it, including the GMRes solver in Julia. So that's maybe one example. The other example is to do some sort of more advanced loss functions where you have some statistical operators. I find that this can be very confusing and can be, I think in theory it's possible, but it didn't work very well every time I tried it in PyTorch, whereas in Julia, you implement your favorite function and just give it to Flux. So those are maybe two situations where I think switching to Julia is going to save you time and energy in the future. Any other questions? Oh, shoot. Maybe there's some online. My computer. All right, there's also no questions online. Well, in that case, I suggest that you basically continue playing with these examples, and you have nurse training accounts now, so you basically have a bunch of GPUs for free for a week. Don't mine any Bitcoins, we'll find out. And if you've got any questions, I'm going to be around. Take your data out of the training accounts at the end of the week, please. So by Friday, otherwise, I think it's going to be deleted automatically. So, it's your job to rescue your own data. All right, and with that, I would like to thank everyone for their attention.